Okay, so a lot of things that I'm going to show here have been done in collaboration with, with my group in Bordeaux, but also at the Laboratoire de Météorologie Dynamique in Paris, in the team of François Forger, and with Robin Wordsworth, who is here today and he will speak later today. So this is the outline of my talk. So first, I will try to do a very, very quick summary of how we can today characterize the atmosphere of extrasolar planets. I will be very brief. Unfortunately, I don't have much time. I will discuss a little bit, I will compare a little bit the properties and the qualities of habitable zone planets, so planets inside the habitable zone, around sun-like stars, stars like ours, and the M-dwarfs. What are the differences in terms of observability and maybe in terms of properties like climate? And I will do a little bit of prospects about what can we characterize using the next generation of space telescope, namely the James Webb Space Telescope, for habitable planets. But then what I really wanted to try to do today is to see if there are things that are important for habitability that we can start to study with this growing population of hot objects that sometimes we call hot super-Earths. We don't know really what they are. They are big, rocky or icy planets, bigger than the Earth and very hot. And I'm pretty sure that there is a lot to learn on this planet and on astrobiology. And it's very unlikely, but if I have more time, I will try to scare you with things that have to do with the Grand TAC model that were presented to you by Morbidelli, and about the genericity of water delivery to planets. But I'll see if I have time to do that. So first, very quickly, how can we learn information about the atmosphere of extrasolar planets? Well, we can do that in the case, especially in the case where the planet is transiting its host star. So what you have here is a photometric light curve of a star and its planet. So it's basically the light we receive from the star and its planet in the case where the planet passes in front of the star. So it's a hot Jupiter, it's a big planet, and this is where the planet goes in front of the star, and so the apparent luminosity of the star decreases. And this is the point where the planet is occulted by the star, and what you get here is the zero level. It's the luminosity of the star, and you're losing the emission of the planet. So let's start first with what you can learn during the primary transit. Well, let's assume that your planet has no atmosphere at all. Then the variation of light will be simply the ratio of the planet surface and the star surface, and it will be independent on the wavelengths. Whether you're looking at UV or infrared, you will get the same dip. On the contrary, if you have an atmosphere, which is going to be more or less transparent at different wavelengths, then the depth of the transit, or the apparent radius of the planet, will be modulated in wavelengths by the properties of the atmosphere. So it will be shaped by the molecules in the atmosphere. And this is the kind of things that you get. This was done for HD 189733. It's either one or the other. And most of the features you see here are due to water vapor. Water vapor is really shaping the spectrum of this planet. It's an abundant molecule on this planet. So this is for hot Jupiter, and these little things you see inside, not the circle, but this little point, would be the kind of variation due to the atmosphere of an Earth. So it would be much more tricky to detect. If we go back to this light curve, so this is the secondary eclipse, the occultation. And so for this hot Jupiter, the depth of the transit is about 0.4%, because it's a big and hot planet, so it emits a lot of light. For an Earth, it's much, much fainter. It's 5×10 to -7 for an Earth-Sun system at 10 microns. You can get better contrast ratio if you go to big Earths around M stars. You can reach 10 to the -4, which is very interesting. And so if you measure these transit depths at different wavelengths, actually you can construct the emission spectrum of the planet which has been done for several cases, and you can then compare with models. And another very interesting aspect on which I have worked quite a lot for the last few years is actually if you get a closer look on this part, you see that there is a variation between the primary transit and the secondary eclipse, and this is due to the fact that you see the planets on different phases. So during the primary transit, you see mainly the night side of the planet, while just before and after the secondary eclipse, you see the day side, and they don't have the same temperature. So actually in the infrared, you see an increase of flux from the planet, which is due to the temperature contrast on the planet. So by doing that, you are probing the climate of these worlds. And so this is for a transiting planet, but this actually has been observed, so this is for a transiting hot Jupiter, but this has been observed for non-transiting planets, which of course makes sense, because if you're just on a slightly different geometry, you're losing these two transits, but you still get this part, unless you're in the unlikely situation where you see your planet pole on, but that's very rare. And it has also been done for a transiting rocky planet, which is Kepler 10b, with an amazing photometric precision. So that was my very brief summary of what you can learn on atmosphere. And so one of the questions is that, are we going to be able to do similar things for habitable planets? And for a lot of them, or only a small fraction of that. And that depends a lot on around what stars you are looking. And Stefan already discussed that. So now I will just briefly compare the kind of properties we have for habitable planet around the Sun or around an M-dwarf. So of course, the original idea was to look for Sun-Earth analogs, and it makes sense. We know that at least life evolved on Earth, so maybe there is something special with this couple, Sun and Earth. We could also push that further away and look for suns that also have a Jupiter and a Saturn system, and then look for an Earth, I don't know. But it made sense, at least at the beginning, to look for really analogs. The problem with the current method is that transiting planet in the habitable zone of Sun-like stars are rare because the probability to have the right geometry is low. So statistically, they will be found far from the Sun unless we are very lucky. And they will also, as I show you, they will offer a very weak contrast ratio with the star, which made them difficult to detect and characterize in combined star plus planet light. So these kind of planets, unless we find a very, very smart way, they seem to require the kind of very ambitious mission like Terrestrial Planet Finder, Darwin, a New World Observatory that were actually very motivating for people like me who went to this field because of this perspective, which is no longer currently in the horizon of space agencies, but you never know. But if you want to know about these planets, at some point, somebody will have to be ambitious and to, I don't know, to talk about big money. What is interesting about M-stars? Well, the first thing is that most stars are M-stars. So if you are interested in the distribution of life in the galaxy, you can't avoid to discuss the case of M-stars. Most stars are M-stars. The good thing is that planets in the habitable zone of M-stars are detectable by current techniques, either radial velocity, as it was demonstrated for the Gliese system. If we are able to find the planet C and the planet D, it means that we should be able to find something anywhere in between, unless it's too small. And also, you can search them by looking stars after star for transiting objects, which is the project EMERS by Dave Charbonneau. Then if you find a transiting planet that is very close, very nearby the Sun, it might be possible to do some rough characterization using James Webb Space Telescope. But it will be very marginal. So it's the half empty, half full glass, depends how you see things. So these contour plots, they show signal to noise ratio with one instrument of James Webb, which is near spec, in transmission spectroscopy. The idea is to detect, it's one of the most favorable cases, you have CO2 in the atmosphere, you want to detect the 4.3 micron band. You have a planet that is transiting at 10 parsec, it's a big one. And this diagram gives you the signal-to-noise ratio for this detection as a function of the stellar mass and as a function of the orbital period. And this is the habitable zone. So you see that it's possible to detect that. I mean, this is not the signal-to-noise ratio on the flux. It's the it's the SNR on the detection itself. So everything above 1 in this case is okay. But it costs a lot. This is the corresponding fraction of the whole James Webb mission as a fraction of time you're spending on it. So let's say that you want to characterize a planet around here. You would have to spend a few % of the whole mission watching transit after transit. Every time there is a transit, you have to watch. You have to watch just also a little bit before and after. And it's a lot of time. So I don't know if we can hijack James Webb for that long. I don't know. And actually, if you look at, this is for transmission spectroscopy, primary eclipse spectroscopy. If you look at, with another instrument, MIRI, if you look at secondary eclipse spectroscopy, you get very similar numbers. So, in summary, the characterization of habitable planets with James Webb, that requires a large habitable planet transiting a nearby M star. And we don't expect very many of that. This is the cumulated number of transits that we expect as a function of distance for different frequency of planets. So every star has one planet, 1/3 of planet, 1/10 of planets. So statistically, in the most optimistic case, the first transits could be found at around 7 parsecs. And at 7 parsecs, if you take the previous few graphs, you can actually get some atmospheric features if you spend 2% of the nominal time of James Webb. What I think is that these questions that are related with the habitability of M-star planets, we should be able to start studying them, try to answer them partly by studying hotter planets. And these questions are the question of the atmosphere survival. How much atmosphere are eroded by strong extreme UV, X-ray, stellar wind? So it's probably dependent upon the stellar type, the stellar age, the orbital distance, and the gravity of planets. And that you can already start to study that with closer planets. These planets are tidally evolved, which means that their rotation is influenced by tides, and they're likely to be found in either a synchronous state, if they are circular, or if they're eccentric, in spin-orbit resonance, or in pseudo-synchronization rate. And some of them are eccentric. So all the properties that the climate should have under these conditions can already be studied if we can observe hotter planets. And one of the big questions is that these big terrestrial planets that we found around small stars, it's kind of weird. If you think about the sun, it's a big star. It has much smaller planet than Gliese D, at least in the habitable zone and the terrestrial planet domain. So what are they made of? Are they like kind of aborted cores of giant planets that have migrated? And in this case, they are made of maybe cometary material, and they are full of water and volatiles, and may not be, there might be too much of volatiles, and they might not be habitable. Also, this kind of thing, I think, that can be studied. So these are the known exoplanets, or part of the known exoplanets. And usually, you have this diagram with mass and orbital distance. Here, I changed and I put the temperature in temperature of the Earth unit. So here you would have the Earth at 1 and 1. You would have the Earth here. And you can see different populations. So here you have the first planet that have been found, the hot Jupiters that cluster in this part of this one is the easiest to detect. Then you have the real Jupiters that are much colder, but still very massive. Jupiter is around here. And you can see that you have this population of hot, low mass, or depending on which direction you're looking at, low mass or big Earth planets that are very hot. And that's actually interesting because this is the observational bias makes that in this part, you're pretty sure that you're finding all the planets around the stars you're surveying. But here you only see the top of the iceberg. And the iceberg is probably very big. So if you close up on this region, so here is a scheme of the habitable zone. So you have in the green, the habitable zone where you need CO2. the one in which we are, so you need some greenhouse gas in addition with the water, and the very tiny part where water vapor can be enough as a greenhouse gas. And these are where the planets are. And you can see that the most interesting ones are around M stars. The Gliese 581 planets, the Gliese 1214, the Gliese 876 are M stars. And this population is just really the top of the iceberg. There will be much more. For this planet, as Stefan showed, you can already start to probe their, not probe, but to have an idea of their composition. So you can make the difference at least between the volatile poor that are below this line and the volatile rich that are above. Whether this volatile is water, a mixture of water and hydrogen, or hydrogen, we don't really know, especially because this line is very, very uncertain, because we don't know the equation of state of water at high pressure, high temperature. There are orders of magnitude of uncertainty, so actually this line can move by a lot. But you can already start to learn things about composition of planets. Then if you go back to this habitable zone diagram, we don't really know the frequency of these planets or the frequency of these planets, but we know that around here there are more than 20% of stars that do have short period, big terrestrial planets. So we know that from radial velocity, and we know that from Kepler. So we know that planets in this region are very, very frequent, although there is no in the solar system. So, of course, we are going to unveil the population with time because we are going to probe longer and longer period. And in this direction, I don't really know. It's more tricky to go to the habitable zone of M stars, but I'm pretty sure that observers are going to find ways to do that. Okay, so the first conclusion is that there are plenty of hot terrestrial planets to study, not habitable in the sense, but that we think of, but they are interesting and there are things we could learn about habitability. But again, the problem is that only a small fraction of this planet do transit. And so transiting ones are statistically far. It's a better situation than for habitable ones, but still, we would like to be able to study with 20 to 50 or even more percent of stars having these kind of planets. They are just next door. But they are not going to transit. Most of them are not going to transit. So we would like to learn still some things about them. So what could we do? What could we do? So a thing that has been one of my hobbies for the last several years is to study what we could do with phase curve. And phase curve is just the photometric variation that you get from the fact that the planet is showing you different phases along the path of the orbit. So this has been observed for non-transiting hot Jupiter, which I don't remember which one it is. It's Epsilon Andromeda, I think. Yes, Epsilon Andromeda. And the good thing is that actually, if you think about the transiting geometry, where the observer is in the same plane as the planet, actually most planetary systems have a high inclination, very close to the transiting one. Half of them have an inclination that's above 60 degrees. So transiting is 90. And half of them are above 60. Nearly 90% of them are above 20. And actually, the phase curve depends very weakly on the inclination in this range of inclination from 90 to 20. So actually, if you change a little bit the inclination, you're not going to change very much the phase curve. And phase curve have a very, very powerful way to study climate. And you can, at first, make easy. You can see the difference between the planet that has no atmosphere, like a big moon or a big Mercury, and the planet that has a dense atmosphere. So first, if we take the case of the moon, the infrared phase curves will follow exactly the phase of the planet. Let's say that there's no big difference between the visible phase curve and the infrared phase curve because the hot part of the planet is the substellar region, is the irradiated, is the starlit hemisphere of the planet. When you start to have an atmosphere, for instance, in the case of Mars, you start to have slight difference. Oh, sorry. You start to have slight differences between infrared and visible. And to study that, you need to have a circulation model for the atmosphere. And you could do that for a denser atmosphere. And actually, if you look at the Earth, the variation that you see are not due to the phase, but to the seasons, so summer and winter. One of the problems, if you're looking at the Earth, that has been a problem for a long time when we were thinking of Darwin, is the fact that actually when you're looking at the Earth, the variation that you see are more due to the moon. So that's the variation, the little black curve is the disk-integrated phase variation of the infrared flux of the Earth, which is very small. And if you look, for instance, at the blue curve, it's the Earth plus the Moon as a function of the observation geometry. So for nearby planets, hot planets, dynamics tell you that you don't expect to find satellites there. So that's at least something that you can get rid of. So to study the phase curves, we have developed two kinds of models, GCMs, so circulation models, and thermophysical models for planets with no atmosphere. And we can study the climate of these worlds and also the observables that you see. So we can study the climate or the phase curves of eccentric planets. I have to go fast. We can study the properties of tidally locked planets, and if you have an atmosphere, there is this risk that there is a collapse here on the night side of the planet. You have the problem of planets with no obliquity, where there is this very cold spot at the poles, where you can have the atmospheric collapse. And we can also study how to characterize planets. So for instance, if you look at different atmospheric pressure, this is how the planet will look like at 9 microns. And so there is a dependency on the pressure. For a given pressure, you can look at 3 adjacent bands and see that there will be a big difference because you are actually probing different parts of the atmosphere. So you can do this kind of maps. Here you have the wavelengths. Here you have the phases. This is no atmosphere and different pressure. And you can see that you have this kind of black body-like curve or map. And then you start to see the absorption features of the atmosphere and also the redistribution of the heat towards the night side. And the good thing is that actually if you do, even for a non-transiting planet, if you do a spectrum of the amplitude of the variation, if you have no atmosphere, so the amplitude spectrum is the dashed line, and the red, green, and blue are the real spectrum of the planet at different phases. If you do, in photometry and relative photometry, the amplitude spectrum at different wavelengths, you can build a kind of equivalent spectrum of the planet that is also shaped by the molecules. And you can also measure the size and the mass of the planet this way by combining with radial velocity. You can measure rotation rates of planets if they have no atmosphere, so you can test tidal models. And, well, I think I have to stop around here. Sorry for being quick at the end.